This is Parents Podcast number 69, and today we have part 2 of Flying Animal Aerodynamics. So if you haven't listened to part 1, that's podcast number 68. Listen to that and then come back to this and listen to the second half. In this second half, we're going to be focusing on the same paper, The Flight of Birds and Other Animals, which is an open access paper, and you can access it in the link in the description. But we're going to take off from where we left off before. So we're talking about how much energy it takes for animals, for these birds to fly, and how they use their fat stores to fly that amount, and the amount of fat they have on their bodies when they start flying, which for one particular bird, it was 55% of its body was fat. So, and then by the end of their flight, they are much thinner. So let's move on to feathered wing flight. So now we're going to talk about the different types of wings. So not only feathers, but also the bat type wings and the pterosaur wings. Let's start off with the feathered wings. So the bird skin structures, the feathers, are often said to be just another variant of a modified reptile scale. And that may be so, but they are made of different proteins compared to other reptile scales and have some of their own special properties. So feathers are the only known skin covering structures that contribute directly to the structure of the animal and have nothing to do with the vaguely fibrous feather-like structures seen in fossils that are later in time than the earliest birds, so Lower Cretaceous period. So that they assume that, they think that they're modified reptile scales, but they do have their own function, which nothing else on Earth, present or past that we know about, does the same thing. So they say that the shafts of a bird's wing feather forms a spar, which collects up the forces caused by the airflow on each feather and sends it through the feather's root to the bony skeleton. So each feather has that central shaft bit, and that's effectively a part of a bigger spar, or you can think of it as many spars, which then add up to one larger spar. And as I went through in the last podcast, spars are the terminology that we use for aircraft. So a fixed wing, if you have a regular wing on, let's say, a 737 that you're flying on to go wherever you're going, the wing has a central beam in it, and often they have two beams, but there's usually one which is like the main load-bearing beam, and then they might have another one or two supportive ones. Then you have at 90-degree angles to that main beam these other beams called ribs, but this main spar is the main load-bearing part of the wing. And it's quite funny because when I was doing my undergrad, we had a wing from a Cessna, and we could load it up and see how the strains on the beam on a spar would occur. And then, but if you load it too much, then it breaks, which is what happened. Not my group. We were good. Another group, they broke the wing because they put too much loading on there. So they can break, but if they're well designed, then they're loaded the proper way, they will never break. So, moving on from that little tidbit, the bird wing is a distributed spar and not a tension wing as seen in bats and pterosaurs. The feathers do not only form the structure of the wing, they determine its aerodynamics as well. So the unusual shape of feathers is so distinctive that the first known bird feathers from the earliest bird fossil, the Archaeopteryx, was known as the feather in the mid-19th century and was identified as coming from a bird long before any other parts of these fossils were known. So it has a central rachis, they call it, which is the shaft, and it's shaped to collect the bending and torsional moments developed by the veins and deliver them through to the root of each feather to the bony skeleton of the arm. So that's interesting that the feathers in these arms actually pretty much attach to the bone, and they transfer force that way. Now, this is interesting. If a feather is lost, there is a gap in the wing, but the whole wing continues to work, unlike a bat or pterosaur wing. So if with a bat or pterosaur wing, which is a tensioned wing, if you take a part of that out of the bony structure, for example, the entire wing will collapse. So the whole structure of the bird wing made up of feathers can be shed by molting once per year or even more often and replaced. So that's pretty cool. And now they have a really cool figure, which is if you're listening to this, you can always see the video on YouTube. We have our podcast on there with the video. They have the feather of a grey goose. It's called a secondary flight feather, and it's made of keratin and has a second moment of inertia plotted against it. So the second moment of inertia determines how stiff an object is in that direction. So if you have it in the y direction, then if you try to bend it in the y direction, if you have a very high second moment of inertia, it means that it's stiff and it will take the loading very well. Now, this is a very important part for structural engineering. And they have the second moment of inertia in the x and y directions along the bird feather. Interestingly, when you're very close to the root, the bending moment in the x direction, so in the free stream direction effectively, is significantly greater, about twice as great as in the y direction, so the up and down direction. So that's interesting. It means that this feather obviously has been has evolved to be stiffer in this direction because that's probably where the loading is greatest at this point. Now, I wonder if, depending on where the feather is, the second moment of inertias would change, like the distributions. Like if you have a feather at the leading edge, if the way that the second moment of inertias change as you go across the feather, that might be different to if you have a feather at the trailing edge, or whatever, or near the root or near the wingtip. So near the root, as I mentioned, the feather is stiffer in the x direction by about a factor of 2 than in the y direction. When you get to the midpoint, that relationship pretty much reverses. So now it's about twice as stiff in the y direction as it is in the x direction. Oh no, sorry. No, that's right. So I'm sorry, I made an error in that. In the near the root, the feather is stiffer in the y direction than the x direction by a factor of 2. And the midsection, it's the opposite now. So in the x direction, the wing is about twice as stiff as in the y direction. Sorry about that confusion. I'm still mastering the use of numbers. Then by the time we get to the wing tip, the second moment inertias are about the same in both directions. So the feather is about as stiff in either way. But also from the wing root to the wing tip, the stiffness reduces, so it gets weaker, as you'd expect, because the closer you get to the wing root, the more accumulative loading there will be, because it has to transfer all the force to the actual central bone structure of the bird. So I thought that was quite cool because you rarely see the second moment of inertia of feathers. Let's move on to tension wings. So we covered feathered wings, which we know from birds. Now let's look at tension wings of bats. So they say there is another type of modern wing, that of bats, which started from nothing after the loss of the dinosaurs and developed alongside the post-dinosaur birds. So it allowed, from other research, they've put fruit bats into wind tunnels, and this allowed three-dimensional stereo pictures of the wing membranes, which were good enough for rough lift and drag analyses and showed gliding performance much like a pigeon. So several species of small insectivorous and nectar-eating bats have been flown in the Lund wind tunnel. I mentioned that wind tunnel in podcast number 68 and some of its specifications. And they did this in this wind tunnel to mainly look at the wakes and PIV. So the bat wings are held in shape by a skeletal framework. So let's scroll down to have a look at it. So I'll zoom out here. If you look at like a regular bat, interestingly, the entire wing goes from the bat's shoulder to the ankle of its foot. And the actual wing itself, the bone structure in it is its hand. And then each of the bones coming off there are each one of its fingers. So it has 5 fingers like a human, and these fingers are of different lengths depending on how far they go along its wing. And then its arm is also part of the wing structure. So all these membranes, like there's a membrane that goes from its wing shoulder, which is sort of cordoned off by its arm and then its thumb. And then there's another wing membrane between its thumb and its index finger, then another one between the index finger and the middle finger. So it could actually give the middle finger to people if it wanted. It couldn't, because it's all tightly grouped with everything else. It couldn't move it individually, I don't think, enough so you'd even know that it's doing it. So anyway, and then there's another membrane between the middle finger and the fourth finger, the ring finger, and then from the ring finger to the pinky, there's another membrane. And interestingly, the pinky finger is one of the biggest ones. And then there's another membrane from the rest of its body to the pinky finger. So there are these independent membrane structures. And there's also a little bit of hair on the bat. I'm guessing that's probably for some sort of aerodynamic benefit. Considering where it is, it's probably to turbulate the flow a little bit to make it resist stall, and so it can fly at greater angles of attack and produce more lift. Let's get back to some of what they were talking about here. They say bat wings are held in shape by the skeletal framework structure, stretching a membrane that has no stiffness on its own and is not stiff in itself compared to birds. So that's interesting. The membrane is just like a sheet of plastic, you can kind of think of it. Now, in flight, the platform has only a limited degree of variability of shape because relaxing the muscles that hold the framework in shape also takes the tension out of the main membrane. So that's interesting. For a bat, if it tenses its muscles, that makes the membrane go tight. So you can change how loose the membrane is, I guess, and that will change the flight performance. So bats have a wholly different system of muscle fibers in the membrane, which tighten up to reduce its curvature without connecting to the skeleton. That is interesting because most muscles, as far as I'm aware of, have to kind of be attached to the bone or some kind of ligament or tendon or something to work. These obviously have a slightly different way of working where they don't have to really be connected to a bone, but maybe they're connected to tendons or ligaments. I'm not sure. If you know, let me know in the comments below. So their wings are exceptionally good at low-speed maneuvering flight, but are not general-purpose wings, adaptable like those of birds for swimming, running on the ground, catching other birds in the air, and so on. So birds are far more capable flyers than bats. Birds use every kind of habitat known to mammals, whereas bats are fruit and honey eaters and catchers of slow-flying insect prey. So bat eyes do not dominate their skull, and they are mostly nocturnal animals with senses that are based around hearing. So bats can be as big as small geese, actually, and do not reach the size of swans. Actually, I beg to differ on this point. So where I used to live at one point in my life, they had these things called flying foxes, and if you know what they are, then you know that they're massive. So I lived near a river that went through the city, and during dusk, often these massive bats would be flying around. You to see them though, and they're huge. Like their wingspan is close to a meter, and the actual bat itself, the body, looked to be about 30 centimeters long. So, and interestingly enough, in this river there were also swans. So it was a pretty easy way to compare the size of them, and just the actual physical volume itself of the area. The bat was much bigger than the swan in terms of weight. The swan's probably much bigger than the bat. Like the swans maybe 30 or 40 kilos, whereas the bat was probably maybe 10 kilos. But it depends how you look at sizing. If you look at the actual volume of the bat, it was much bigger than a swan because their wingspan was huge. So let's move on. So the final animal that we're going to look at are pterosaurs. And pterosaurs are effectively the original flies that we all know, like the dinosaurs, like the pterodactyl. So they say it would be an error to think of birds as being permanently the best flying animals, although they have held this position for some millions of years. We don't want to be an error. So let's cover these animals too. So the modern time began in the Paleocene for birds, when a few birds survived from the disaster that finished the dinosaurs, probably an impact with a small asteroid about 65 million years ago. Actually, on this topic, this doesn't have anything to do with aerodynamics, but it's geology based, but I thought you might be interested. So when I was doing geology, one of my professors, he was world renowned. His name is Professor Plimer, and he was saying, this was back like 10 years ago or more, actually more, 15 years ago perhaps, that back then everyone was saying that the asteroid was what killed out all the dinosaurs. But he said, no, it's probably a supervolcano. So supervolcanoes are like nothing we've ever seen before in our existence, but they are fairly common throughout history. They make Krakatoa look like a little baby one. And then in recent times, I've just been keeping up with the theories on this. And then they're starting to say that it was probably the conjunction of an asteroid and a supervolcano that created the extinction of the dinosaurs. So they're leaning towards the supervolcano angle a bit more. And I'm pretty sure Professor Plimer was right. So it probably was just supervolcano. Anyway, I thought that was interesting. So the rivals of the early birds, the pterosaurs, disappeared from the fauna along with all the remaining dinosaurs, never to return. The period from about 250 million years ago up until 65 million years ago followed the Great Extinction, which ended the preceding Permian period. At some time in the Triassic period, which followed the Great Permian extinction, both the birds and the pterosaurs started from scratch as non-flying arboreal creatures living in the trees at the time. So I didn't know this, but birds and pterosaurs actually were around at the same general time period, and they would have been seeing each other too in the trees. So their anatomy, pterosaurs, pterosaurs and birds are radically different from the start, showing the contrast between the multiple spar wing built around feathers for the birds and a tension wing seen in pterosaurs. So the pterosaur wing is made up from a flexible protein membrane, which, unlike feathers, has no strength to resist the bending or torsional moments developed by a wing. So, like a bat, without the actual bony structure around it, the wing can't do anything. Whereas with the feathers, they each have their own little load-bearing structure to it. So the resistance to these forces comes not from the wing itself for these pterosaurs, but from the bony framework surrounding it. And they say that this bony framework made up from the side of the body to the arm skeleton, which had just one extremely elongated wing finger along the leading edge. So this is a nice little juicy tidbit. The pterodactyl, the dactyl part of the word, actually refers to the Greek word dactylo, which means finger. So most of the leading edge of the pterodactyl wing and the pterosaur wings in general is actually just the pinky finger that's been extended like crazy. And then only the wing root part is where the actual arm is and the rest of the hand. And then, so that pinky finger is taking up pretty much all this loading that's on the wing. So let's come back to some of what they're saying. So the wing of pterodactyls and pterosaurs in general was held in shape by muscles controlling the body framework, and when these muscles relaxed, like in death, the wing simply collapsed. So it's like a hang glider wing, but not like a bird wing, which does not collapse when the bird dies. So they say that it had an elastic membrane which was pulled into shape by the muscles and required the side of the body to be suitably shaped to hold its position. So I'm pretty sure the entire bony structure was required and the body was part of this entire structure. Whereas the bird wing shape does not depend on the shape of the body or legs. So the astonishing thing about this is that the very same German Jurassic rocks from Solnhofen in Bavaria that held the fossils of the Archaeopteryx, which was the first known bird, also held a good selection of pterosaurs from the same time and habitat. So this means that they existed at the exact same time, two different types of flyers, which isn't that weird if we think about insects, birds, and bats all exist in our period as well. So they have different ways of flying. So they say this was not the end of the pterosaur time, but the middle. And the really big pterosaurs were then still millions of years ahead in the future. So it's interesting that the larger pterosaurs were later, towards the extinction part, they grew to that size. So how then did birds and pterosaurs carry on side by side through the Cretaceous period of time, another 60 or so million years, which ended with the destruction of the dinosaurs and pterosaurs? Why did not birds with much better wings replace the pterosaurs? And then the author there says, in his or her view, I don't know, I can't remember the name. Anyway, in his view or her view, there is a reason for that, and it is to do with the automatic homing system that modern birds have built into their brains. So modern birds and birds back then have a time sense that will keep track of time within seconds for months at a time in the absence of external stimuli, and the ability to do trigonometry relating a currently observed plane, so the horizon, to a world-sized sphere. That is all it takes to navigate anywhere on Earth. So I'm guessing birds are not flat earthers. They actually believe that the Earth is round, and they probably have seen it. So it is not likely that just one group of birds could do that at the time of the loss of the dinosaurs, and that they were the only ones that were able to survive and become the ancestors of all modern birds. So that's in this podcast. Make sure to like, subscribe, and check out the atmosphere hawk, which is the instrument we do make to make your experiments easier. It accurately measures the density of air, so that takes that error out of your experiments. Also, if you want to get better at theory of aerodynamics and CFD and experiments, we do courses. Make sure to check them out. Links in the description. See you next podcast. Peace out, amigos.